Objective 5. We want to find the exact values of the trigonometric functions of an angle given one of the functions and the quadrant of the angle. So many problems will require finding the exact values of remaining trigonometric functions when one of them is known and the quadrant can be found. When we want to do this, we can use two approaches. We can either use a circle of radius r, or we can just use our identities, which, remember, may need to be rearranged. So let's go ahead and do an example. So given that sine of theta is equal to 1/3 and cosine of theta is less than 0, we want to find the exact value of each of the remaining 5 trigonometric functions. So let's start with our first method. Because we use two approaches, we can use a circle of radius r, or we can use identities. So we're going to say that using a circle of radius r is going to be method 1, and using identities will be method 2. And for this problem, we're going to go through both methods. So method 1, this is using our radius, or using a circle. Radius r. All right, so using a circle of radius r and looking at our image here, if we know that sine of theta is 1/3 and cosine of theta is going to be less than 0, we want to find the exact value of each of the remaining 5 trigonometric functions. If we want to use the radius, we know that if we have a radius that is not 1, then sine of theta would end up being y divided by the radius. So, assuming that's what's going on, we can say that sine of theta would end up being 1 if our circle had a radius of 3. So, we can say that since sine of theta is equal to y over r, we can assume y is equal to 1 and r is equal to 3. Also, if you're really thinking about graphing this equation here, we also know since since sine of theta is equal to 1/3, which is greater than 0, and we know that cosine of theta is less than 0, this means that we're looking at y values that are positive and x values that are negative. And this is going to tell us that our point P is in quadrant 2, which is what we had conveniently written out with our picture here anyways. So the picture was written beforehand, but this gives us a hint. It's going to be in quadrant 2. So we're looking at a picture here. We see our radius is 3, our point is in quadrant 2, and we see we have a circle. We can use the equation of a circle to go ahead and solve for our values, specifically x, since we already know what y is. So we can use the equation of a circle to find x. So we're saying that x squared plus y squared is equal to 9. So x squared plus 1 squared is equal to its radius squared. In this case, the radius is 3. So it is 3 squared. So x squared plus 1 is equal to 9. Subtract 1 from both sides and we get x squared is equal to 8. So we'll go ahead and take the square root of both sides, and we get x is equal to the square root of 8. Remember, normally we would write positive or negative version of 8, but we know that cosine of theta is less than 0. So x has to be negative. So x is equal to negative square root of x, sorry, square root of 8, which we can then simplify. Since this is technically 2 times 4, we can simplify this to negative 2 times the square root of 2. So now we have our values of x and y and r, so we can solve for the rest of our trigonometric functions. And I'll write trig for trigonometric. So we have x, y, and r. We already know that sine of theta is 1/3, but remember sine of theta was y over r. Cosine of theta is x over r, so we're getting negative 2 square root 2 over 3. Tangent of theta is y over x. So this is going to end up being it's y over x, so y is 1. And x is negative 2 square root 2. So then we can go ahead and simplify this. We have to multiply our numerator and denominator by the square root of 2. This gives us negative square root of 2 over 4. And let's scoot over a little bit. Then we can do cosecant of theta, which was r over y. So that would be 3 over 1, which is just 3. Secant of theta, which is r over x. So this would be 3 over negative 2 square root 2. Multiply the top and bottom by the square root of 2. And this is going to end up giving us negative 3 times the square root of 2 over 4. Then cotangent of theta is going to end up being negative 2 square root of 2 over 1, which just simplifies to negative 2 times the square root of 2. So these would be the values of our 6 trigonometric functions. And that was using method 1. So that was using a circle with a radius of r. So this wasn't using any identities. And now we want to go ahead and use our identities. So we're going to write method 2 over here. We're going to make it a little smaller. So for method 2, you want to use identities. And since we already know what sine of theta is, by using our identities, we're going to solve sine squared of theta plus cosine squared of theta equal 1 for cosine of theta. Because we know what sine of theta is, now we want to know what cosine of theta is. So if we have sine squared of theta plus cosine squared of theta is equal to 1, we're solving for cosine. We'll subtract sine from both sides. We get cosine squared theta is equal to 1 minus sine squared of theta. Take the square root of both sides, and we get cosine of theta is equal to positive or negative square root of 1 minus sine squared theta. And remember, we write plus or minus because that's technically correct, but we know that cosine of theta is less than 0 from our problem. So this will be negative. So now we're going to plug in sine of theta is equal to 1/3. So we have cosine of theta is equal to negative square root of 1 minus sine squared of theta. So this is going to be 1/3 squared. So simplifying, this is going to be 1 minus 1/9, which we can then rewrite this as 9/9 minus 1/9, which gives us negative square root of 8/9. If we take the square root separately of the top and bottom, this ends up giving us negative square root of 8 over square root of 9. We know that the square root of 8 is 2 times the square root of 2, and the square root of 9 is going to be 3. So now we have the value of cosine and we have the value of sine. Cosine of theta being the value with our radius. So this means y is equal to 1 and x is equal to negative 2 times the square root of 2, and then we get the same identities. Since we got the same values of x and y, this results in the same identities as in method 1. So when you're doing problems like these and your homework quizzes, tests, anything like that, you can pick whichever method that you like best. You, by all means, do not have to do both methods for each one of these problems. Whichever one you find easier to work with, that should be the method that you use. Just know that either method you use, you will end up with the same answers. By the looks of it, method 2 is a little shorter, a little simpler, but if method 1 makes more sense to you, then by all means, use that one. I clearly thought there was going to be a lot of work there. So then there is a walkthrough of the two approaches. So this is found in your book. You can feel free to pause the video at any time, copy this down. But when you're finding the values of trigonometric functions of theta, when the value of one function is known and the quadrant of theta is known, then given the value of one trigonometric function in the quadrant in which theta lies, the exact value of each of the remaining 5 trigonometric functions can be found in either of 2 ways. So option 1, using the circle of radius r. For step 1, you draw a circle centered at the origin showing the location of angle theta and the point P that corresponds to theta. This was already done in our problem. The radius of the circle that contains P is radius is equal to the square root of x squared plus y squared. Then you want to assign a value to 2 of the 3 variables x, y, and r based on the value of the given trigonometric function in the location of P. Then step 3, you want to use the fact that P lies on the circle x squared plus y squared equals r squared to find the value of the missing variable. And then step 4, apply the theorem on page 386 of your book in that case to find the values of the remaining trigonometric functions. So that would be our equations for finding values of our trigonometric functions with circles of different radiuses. Option 2, use identities. So option 2 would be just use the appropriate identities to find the value of each remaining trigonometric function. So fairly straightforward there. Then lastly, our last objective here, objective 6, we want to use even odd properties to find the exact values of trigonometric functions. So recall that a function is even if f of negative theta is equal to f of theta for all theta in the domain of f, and a function is odd if f of negative theta is equal to negative f of theta for all theta in the domain of f. So we say the function is even if the value of your function with a negative theta is the same value as your function with a positive theta, and it's odd if your function of a negative theta is equal to negative function theta. So we can determine if our trigonometric functions are even or odd, fairly straightforward. So For our even odd properties of our trigonometric functions, we see that sine, cosine, tangent, and cotangent are all going to be odd, which means that sine of negative theta is equal to negative sine of theta, cosine of negative theta is equal to negative cosecant of theta. I meant cosecant if I accidentally just said cosine. Cosecant of negative theta is equal to negative cosecant of theta. Tangent of negative theta is equal to negative tangent of theta. Cotangent of negative theta is equal to negative cotangent of theta. Then we see that cosine and secant are our even functions. So cosine of negative theta is equal to cosine of theta, while secant of negative theta is equal to secant of theta. So if you want to just remember, cosine and secant are the even functions. Everything else is odd. So for our example, we just want to find the exact value of each of the following angles. So for A, if we have cosine of negative theta, well, we know that cosine is even. So cosine of negative theta is equal to cosine of theta. You may have noticed that sometimes we do write parentheses around a theta for sine and cosine for our trigonometric functions. It is up to you whether or not you like to use them, but either way, they mean the same thing. And we're going to scoot this over so there's more room. All right, so cosine of negative theta is equal to cosine of theta. So if we have cosine of negative pi, that tells us that cosine of negative pi is equal to cosine of pi, which cosine of pi is just going to be equal to negative 1. So cosine of negative pi is equal to negative 1. So really for these problems, you're just determining if the equation is even or odd, and then going ahead and fixing it. So for cotangent is odd. So cotangent of negative theta is equal to negative cotangent of theta. So we see that cotangent of negative 3 pi squared, that's going to be a negative value. So cotangent of negative 3 pi over 2 is going to be equal to negative cotangent of 3 pi over 2. The value for cotangent of 3 pi over 2 is going to end up being 0. So technically this is negative 0, but that's just going to be 0. So cotangent of then negative 3 pi over 2 is just going to be 0. So for these problems, you're just identifying if it's even or odd and just making sure that basically your final answer has a negative or not. So all right, that wraps up our section 6.3. So I'll see you again in section 6.4.